Hello everyone! Java 21 will be released really soon in September 2023. Today, let's discuss what are the main features it will bring to the language. First, Java 21 will be an LTS release, which stands for Long Time Support. It means that both bug fixes and security patches will be applied to Java 21 for a longer period of time. Usually, Java that is used in the production environments is exactly an LTS release. That's why we usually see the Java 8 or 11 or 17 in production. So, in my opinion, Java 21 will be heavily used in production in the course of the next 5 years, and that's exactly why we should understand what it brings to the language. If we go to the OpenJDK page, we can see 15 JEPs or Java enhancement proposals that were selected to be delivered in Java 21. 7 JEPs are in preview or incubator state, which means that their APIs can change significantly or even the whole feature can be removed. So we will skip them for now. 2 more JEPs don't bring anything new to the language, but instead they deprecate some existing feature. We will skip them too. And finally, 2 more JEPs are a bit too advanced. They bring some enhancements to the ZGC, a low post garbage collector, and to the key encapsulation mechanism. So today, let's talk about these 4 JEPs. And in my opinion, one of them will significantly change the way how we develop in Java. Let's start with sequenced collections. This JEP isn't really big, and mainly it just brings convenience methods to exist in Java collections. But in some rare cases, it may actually improve the performance of your application. This JEP brings new interfaces to the Java collections framework. All the collections that have an order of elements, so all lists, queues, some sets, and maps, will implement a new so-called sequenced interfaces. Let's see them in practice. Let's say I have a list with 4 elements, and I would like to print the last element of the list. How could I do it before the Java 21? I had to write list.get list size -1. This code isn't really easy to understand when you are reading it in a huge method. Luckily, starting from Java 21, we have a new method, list.getLast. And when we run this code, we can see that both old and new versions print the same correct result, 4. Next, let's say I would like to iterate over this list or get a stream in a reversed order. How can I do it? For Java 21, you had to create a new list of integer, let's call it another list, and to the constructor we will pass our original list. Then we will use a convenience methods of collections class, reverse, another list. And now we can iterate over this another list. For example, we will print each element in the reversed order. Let's run this code. And we see that all elements are printed in the reversed order. Using this another list, I can get a stream of it and do whatever I want with a stream in the reversed order. But this approach with copying collection and reversing it isn't really efficient. And starting with Java 21, we can do it much better. We can call method reversed, which returns a view on our original list in a reversed order. And on it, we can do system out println. And yeah, let's remove this one, run this code and see how it works. Yeah, so it works correctly. And actually we can put this list reversed to another variable and use it as a usual list. For example, we can get a stream of it and it will be in reversed order. I said that list reversed returns a view on the original list. What does it really mean? It means that the changes to the reversed list will be reflected to the original list. So let's add a new element 5 to the reversed list and print after that our original list. And what can we see? The number 5 was added to the beginning of our original list. It works so because we add an element 5 to the end of our reversed list, which actually means the beginning of our original list. After that, we can, for example, remove all odd elements from our original list. And after we print our reverse list, we can see that all odd elements were removed from it also. Now let's actually go to the sequence collection interface and see which methods it adds. So it adds reversed, add first, add last, get first, get last, remove last methods. Pretty simple. And if we go to the sequenced map interface, we can see that it adds similar methods. So it adds reversed, first entry, last entry, pull first, pull last, which actually removes the entry from the map, put first, put last, and three methods to get a sequenced set or collection of the keys, values, or entries. And if we finally go to the sequenced set interface, we can see that it doesn't add any new method, but instead it overrides the reversed method to return sequenced set instead of sequenced collection. This JEP doesn't bring a lot of new features, but in my opinion, it will improve the readability of code that uses collections that are now actually sequenced. Next, let's talk about recurrent patterns. This feature isn't very big either, and it's quite hard to explain it. So let's see it in action. Let's say we have an interface shape and two records, circle and rectangle, that implement this interface. Circle has a one field radius and rectangle has two fields, width and height. And we would like to write a method that will print a message based on the type of the shape that we passed to it. If it's a circle, we write it's a circle with radius. And if it's a rectangle, we write it's a rectangle with width and height. This is the way how you wrote this method before Java 17. The code is kind of clumsy and ugly, but Java 17 brought a small enhancement to this code, and even the IDE suggested to me right now. We can write if shape instance of circle circle, and if this condition is met, the Java will automatically create a variable of type circle and cast the shape to this variable. And we can do the same thing with the rectangle. So this code looks much better. But with Java 21, we can make one step further. Instead of writing if shape instance of circle circle and then getting its field, we can deconstruct the record to its fields. So we write if shape instance of circle with double radius, and then we actually use this radius in the if clause. The IDE doesn't understand that I'm using Java 21 features, so it marks this code as a compile time error, but it will actually work. And we can do the same thing with the rectangle, so we will use double width and double height. And we can use them in the if clause. Now let's call these methods twice with the circle and rectangle and see what happens. Yep, so we see that this method works and it prints different and expected messages for both circle and rectangle. Let's add one more record shape pair that will contain two shapes. And in our case, they can both be circles or rectangles or one circle and one rectangle, etc. And we will write a method match that will actually work with this shape pair. What we can do, we can match against the real type of shape inside this pair. So we write if shape pair instance of shape pair with circle C1, circle C2. And we can here write two circles, for example. Let's write a second if. If shape pair instance of shape pair rectangle R, circle S, then we can write that it has one rectangle, one circle. So it's a great feature, but can we go any further? Actually, we can. Let's imagine that in the second if, we would like to print the radius of the circle. We can use the recurrent pattern in a nested way. So we write a circle with double radius, and we print one circle with the radius plus radius. And let's run this code. We will make these methods public and static. We will go to the main and call it. with a new shape pair, new rectangle 1 and 2, and new circle 3. And now we run this application. And we can see that it prints an expected line, 1 rectangle, and 1 circle with radius 3. This JEP improves code readability in some cases. I don't think that it will be as heavily used as sequenced collections, but still I'm really glad that this feature was introduced to Java. Next, let's talk about matching for switch. This feature was in development for a really long time, and yeah, let's see it in action. Let's say we have to write a method that will calculate how many bytes an object will take when we write it to the database. And we have it in Java 17 form. First, we check if this object is a string and we just return the length of the string. We assume that all the characters are ASCII characters and they will fit within 1 byte. Then, if it's a long, we return 8 bytes. And if it is an integer, we do additional checks. If it can fit in 1 byte, we return 1. If it can fit in 2 bytes, we return 2. And otherwise, we return 4 bytes. Otherwise, if it's not a string, long, or integer, we throw a runtime exception. This code works and it looks okay, but with Java 21, we can actually rewrite it completely. So here we can write return switch from object, and inside of it we write different clauses based on the type of object that we get. First, let's write case string s. In that case, we return string length. The IDE marks it as a compile time error, but it will actually work. If the object that we get is of type long, we simply return 8. And in case if it is an integer, we write the following code. Here inside the switch, we cannot use the return keyword and we have to use the yield instead. Yield, yields, and yield. And let's write a main method that will test this method. So we instantiate a new instance of this type and we will call methods on it. We print matching for switch, calculate size in dB, some string, then we call it with integer 1 million, let's say, and long 1 million. Let's run this code. And the compilation failed. Actually, we can see that we have to cover all possible input values. And in our case, we have to write a default clause. In the default case, we will throw new runtime exception, for example. Okay, and let's run it again. And we see what we expected. This string takes 11 bytes, number 1 takes 1 byte, million takes 4 bytes, and million long takes 8 bytes. Okay, so it works. Instead of the default clause, we can actually write case object O, and yeah, let's again throw new runtime exception. In this case, it will not actually compile also because we have a catch all clause and the default one, and we can use only one of them. So I can remove the default clause and it will compile and it will actually work. But I prefer the default clause compared to the catch all. This code looks okay, but actually we can do better using so-called guard patterns. We can write case integer I when and put here a condition. When the integer fits in 1 byte, in that case we return 1. When the integer fits within 2 bytes, we return 2. And in all other cases, integer I will return 4. And we don't need that part. Okay, semicolon. And let's run it. So yeah, it prints the exactly same results. Here you can write any condition using variables that are declared to the left from the when clause and variables that are available outside of the switch case. So I cannot use here my long because it's not declared here. And yeah, in my opinion, this code looks much better than it was before. Okay, let's see another example with a matching for switch. Let's return to the interface shape and to records, circle and rectangle that implement this interface. And let's say we are writing a method shape area that calculates the area of the shape that it gets. We can write it using the instance of and record patterns that I showed you before, but actually we can do it in a much simpler way. So here we can write return, switch, shape, and do different calculations based on the type of the shape that we get. If in case it is a circle C, we have to do C radius multiply C radius multiply math pi. Yeah, it seems correct. And in case of rectangle R, we return R height by R width. And here we also have to write the default clause. Instead of it, I will actually write the case shape, so it will catch all the shapes that we didn't catch before. And in that case, I will return just 0. And let's run this main method that calls this shape area using circle and rectangle. Oops, I forgot the semicolon. Yeah, let's edit and run it again. Okay, so it prints the area of both shapes that we passed. Great. But actually we can use the record patterns here. So we can write in case of circle with double radius, we return just radius multiplied by radius multiplied by pi. And with the rectangle, we will call it double x, double y, and we simply multiply x by y, and that's all. Let's run it. It prints the exactly same result. So the matching for switch is a great candidate to be used with the record patterns. And yeah, actually, let's see one more example of the matching for switch. So let's say we have a sealed interface A that permits two records B and C. And yeah, we have these two records that implement the interface. And we would like to write a switch over the instance of type A. And here actually we can write two cases, case B and case C, without writing the default clause or catch-all clause like AA, blah, 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 because the compiler understands that there can be no the instance of the interface itself, and it only permits the classes B and C. And in these cases, we covered all the possible options. We covered the case B, case C, and that's why this code will actually compile. If we run it, we see this is an instance of class B, and when we called this method, we passed here a new instance of B. So the matching for switch is a really powerful tool, especially when you combine it with the recurrent patterns. It improves the readability of the code, it reduces the number of bugs, and in some cases, for example, when you write compilers, it can significantly change the way you write your application. Before proceeding to our last topic, I will kindly ask you to like this video and subscribe to the channel to see more. Finally, we have virtual threads. This is the JEP that, in my opinion, will significantly change the way we develop in Java. First, let's discuss what are the problems with the usual threads. Each thread that you create on the Java level has a corresponding thread on the OS level, and these threads are expensive to create and they require a lot of memory. That's why if an application needs a lot of threads to operate, it usually uses a concept of a thread pool. So during the startup, it creates as many threads as it will need, and then it reuses them. The problem with this approach appears when your thread reaches a blocking operation. There are different kinds of these operations, but the typical examples are the following. Waiting for another thread, for example, using thread.join method, making a request, web request, for example, to another service or to the database, and reading from the disk. When your thread is blocked, it cannot perform any operations before the blocking operation is finished. and it can actually take seconds or even minutes. It's unwise to spend CPU cycles just waiting when the thread will be able to do the job again, so the blocked threads are usually get suspended or replaced on the core by other threads. Because of it, you have to have more threads in your application than you have cores on your machine. In the typical web application, you usually have around 200 threads. Before Java 21, there was only one way how to cope with this problem. It was to use reactive programming. This approach is a bit too advanced, so we will not talk about it today. I just want to say that it solved the problem, but actually it also introduced a bunch of other problems. So on each project, you had to select which drawbacks you would like to introduce to your project. And now we have virtual threads. These are lightweight threads that don't have a corresponding thread on the OS level. When they have to execute, they mount on the real so-called carrier thread. These threads copies the stack traces, the variables, and then executes the code. When the virtual threads encounter a blocking operation, they don't block the carrier thread. They just unmount and allow other virtual threads to be mounted to that carrier thread. Using this approach, several virtual threads can be actually executed by one carrier thread, and you reduce the number of real thread switches on the CPU level. Still, you have to switch between virtual threads, so to make unmount and then mount operation, but this operation should be much shorter than the real thread switch on the CPU level. Virtual threads in Java are represented with a simple object, so they don't need as much memory as the usual thread needs. And well, let's see them in practice. Before seeing actual virtual threads, let's see the problem with the real threads. Let's say I have a long task that basically sleeps for 1 second, but it actually could be a request to the database, another service, whatever. And we have a thread pool with 10 threads that executes this long task 200 times. I will run this application. And yeah, how much time will it execute? Well, we have 200 tasks, each execute 1 second, so it's like 200 seconds split between 10 threads, and the execution time will be somewhere around 20 seconds. And yeah, it's an expected amount of time, but it's not optimal because threads don't do anything. I would like to be able, yeah, it finished. I would like to be able to start 200 tasks simultaneously so they finish within 1 second, maybe a second and a half. And it's exactly what will happen if we change the executor service to the virtual executor service. It can be easily done by changing the new fixed thread pool method to the new virtual thread per task executor. Let's run this application, and what can we see? We see that all the tasks were submitted simultaneously and they all completed after 1 second. So it reduced the execution time of our application from 20 seconds to nearly 1 second. Well, yeah, it is an artificial example. We just slept for a second and you don't really do it in production. But the real application that makes a request to another service, to the database, to the disk, they will have the same effect just in a smaller amount. One of the biggest advantages of virtual threads is that they're simple Java objects. So here we create a new virtual thread per task, and we created 200 virtual threads. But what if I would like to create 1 million threads? Will it work? Actually, yeah. No real server could survive creating 1 million of real threads, but with virtual threads, it's really possible. They will not work within 1 second because of some overhead that virtual threads have, but still it's much faster than using the real threads. Yeah, I will stop it for now, and let's see what else can we do with the virtual threads. I will have a single virtual thread where I submit a single runnable task. First, let's print the name of the current thread. Let's see how it is displayed. So yeah, let's run this application and we see that actually this thread is virtual. We can see this flag. If we call thread current thread is virtual, we will get true in that case. But in Java, you cannot get an access to the carrier thread, to the real thread that executes your code. You're locked within the virtual thread you're sitting in. It actually improves the security of the applications. The topic of virtual threads is really huge and we cannot cover it within one small video, but we have seen the main advantage of the virtual threads. When they encounter a blocking operation, they simply unmount and let other threads to execute. And they require much less memory than the real threads. So you can create millions of threads in the application without worrying. So the virtual threads are really a killing feature of Java 21. Instead of having, let's say, 200 working threads and assigning one of them to each incoming request, we now can create a new virtual thread to each incoming request. And inside this virtual thread, sending HTTP requests or reading the disk can be done in a plain Java code without trying to put it to another scheduler or whatever. You shouldn't be afraid to block this thread. If it gets blocked, well, it will unmount and another virtual thread will actually mount on this carrier thread. So the virtual threads will decrease the complexity of the code that you have to write as a web developer. Also, if you're using a virtual thread in a typical web application that spends a lot of time making a request to other services or the database, virtual threads will actually improve the throughput of your application. So to wrap up, Java 21 brings a lot of cool new features that I'm really looking forward to try in production. If you would like to know about the preview features that we skipped today, just let me know. Maybe we will create another video on them. Thanks for your attention and goodbye.